Hello there, and welcome to Physics with William, where we explore the wonders of the universe in a calm and thoughtful manner. Today we'll dive into something that's both elusive and fundamental to everything around us: energy. It's a force we rely on for just about everything. Whether you're powering your phone, heating your home, or even simply breathing, energy is at the core of it all. But here's the catch. Despite how central it is to our lives, energy remains one of the most mysterious and least understood concepts in physics. Energy is everywhere. We see its effects constantly, but try to pin it down, and it slips through our fingers. We can measure it, feel its presence, and see the consequences of its transfer. But can we truly understand what energy is made of at its most basic level? This question has puzzled scientists for centuries. What exactly is energy? Is it something physical that we can touch? Or is it a concept we've created to explain the way things change and move? What is energy really made of at its core? Before we embark on this exploration, think about it for a moment. Energy is essential to everything we do. It powers the lights in our homes, the cars we drive, and the electricity that runs our computers. It makes things move, it makes things grow, and it even powers our very bodies. But beyond the simple, everyday uses of energy, there's an entire world of science behind it that's worth understanding. And to fully appreciate that world, we need to start with the basics. Have you ever sat still, watching the world around you, and thought about how things move? How do things go from being still to being in motion? Why do we need energy to make that happen? These are the types of questions that bring us to the heart of the concept of energy. So let me ask you, when you think about energy, do you picture it as a physical substance or as something more abstract? Have you ever wondered where it comes from, or where it goes when it seems to disappear? If you're intrigued by these questions, if you're curious about the forces that drive the universe, then you're in the right place. Before we dive deeper, I'd be grateful if you could like and subscribe to the channel. It helps us reach more people who might be just as curious about the mysteries of the universe as you are. Now, let's take a step back and begin our journey. Energy is something we experience every day, yet it often feels as though we only grasp the surface of what it truly is. Energy is not a substance in the traditional sense. It doesn't have mass, nor does it occupy space in the way that objects do. And yet it can do things that matter and mass do. Energy makes things move. Energy makes things change. Energy is what drives the processes of the universe. To truly understand what energy is made of, we first need to break down its relationship with the world around us. What is the connection between energy and matter? How does energy interact with the objects we can see and touch? If we think of the world in terms of matter and energy, we are presented with two key concepts: kinetic and potential energy. Kinetic energy is the energy that an object possesses due to its motion, while potential energy is the energy stored in an object due to its position or configuration. These two types of energy are linked to the movement of matter, but they are not the only forms of energy that exist in the universe. The world is full of other types, such as thermal energy, chemical energy, and even electromagnetic energy. But what do these forms of energy really have in common? What is it that makes them all energy? What connects them to each other and to the universe as a whole? These are questions we will explore as we move forward. Energy is not something that can be isolated in a container like water or air. It's not something that you can hold in your hands or weigh on a scale. Instead, it's an invisible force that is revealed only through its effects on the world. When energy moves or changes form, we see the result in the physical world. Objects move, heat up, or even glow. But energy itself remains something elusive, something that cannot be captured or fully understood in physical terms alone. So, how do we begin to unravel the mystery of energy's true nature? Where do we look to find its essence? To answer these questions, we need to consider how energy works at the most fundamental level. The journey into understanding energy starts not with objects, but with the forces and laws that govern everything around us. Energy is not a thing in itself, but a concept, a way of describing how things change, how forces act, and how nature behaves. But what exactly does that mean? Is energy simply a tool, a shorthand for understanding how things work, or is it something deeper, something intrinsic to the very fabric of the universe? As we continue, we'll look at how energy is not just an abstract idea, but a vital part of the physical world. It's a part of the equations that describe the motions of planets, the behavior of light, and the forces that shape the universe itself. And yet, the deeper we look, the more we find that energy is not just a static force. It's dynamic, constantly changing, constantly interacting with the world in ways that continue to surprise even the most seasoned physicists. Energy, it seems, is far more complex than we might imagine, and while we may never fully understand all its forms and manifestations, the journey to grasp its nature is one that reveals much about the universe itself. So let's start this exploration together. Let's uncover what energy is made of, and perhaps, just as importantly, what it means to us in the world around us. Energy is a concept that feels both familiar and elusive. In our daily lives, it's the force that makes things happen, the invisible hand that drives the motions of objects, the flow of electricity in our homes, and the heat of a fire. But even though energy is fundamental to everything we do, understanding its true nature is something that has eluded us for centuries. It's easy to take energy for granted, to think of it as just a fact of life, something that simply is. Yet, if we look deeper, we discover that the very idea of energy is a mystery, one that science has been trying to unravel for hundreds of years. The quest to understand energy is a quest for the impossible, not because we can't understand it, but because it is so deeply ingrained in the fabric of the universe that it resists any simple, one-size-fits-all explanation. Energy is not something we can see or hold, and it doesn't follow the usual rules we associate with physical objects. We can observe its effects, measure its transformations, and describe its interactions, but understanding what it is at its core is a puzzle that has many pieces that often don't fit neatly together. So where did this idea of energy come from? How did we come to believe that energy is an essential part of the universe? The roots of the concept of energy stretch back to the 19th century, a time when scientific minds were beginning to grasp the first glimpses of a deeper truth about the universe, truths that would change how we thought about everything from motion to light, from heat to electricity. In fact, energy as we know it today didn't even have a clear definition until the 1800s. Prior to that, there were many different ideas about what drove motion, what made things change, and how to measure these changes. Some of these ideas came from philosophers, others from engineers and scientists, but they all pointed to one thing. There was something more to the world than met the eye. In the early days of science, the prevailing view was that motion was simply the result of forces pushing or pulling on objects. But as people began to think more about how things moved, they realized that the simple idea of a force wasn't enough. Forces could cause objects to move, but they didn't explain how or why things continued to move once they were set in motion, or how things could change without any apparent external force acting on them. This is where the idea of energy began to emerge. The term energy itself comes from the Greek word energeia, which means activity or operation. But it wasn't until the work of scientists like James Prescott Joule, Hermann von Helmholtz, and William Thomson, Lord Kelvin in the 19th century that the modern concept of energy began to take shape. They discovered that energy could be converted from one form to another. Heat could be converted into mechanical work, light could be turned into electricity, and so on. But what was energy, really? Was it just a form of motion, or was it something more? Was it a fundamental property of matter, or was it something that arose from the interactions between particles and forces? One of the most important developments in the quest to understand energy came with the formulation of the first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed from one form to another. This idea, also known as the law of conservation of energy, was groundbreaking because it provided a framework for understanding how energy operates in the universe. It meant that the total amount of energy in the universe remained constant, no matter what happened. But if energy couldn't be created or destroyed, what was it, really? Where did it come from? And how could it exist without ever disappearing? As scientists delved deeper into the nature of energy, they discovered that energy wasn't a physical substance in the way we typically think of matter. Instead, it was a measure of an object's ability to do work. It wasn't something that could be directly observed or touched, but rather something that could be inferred from its effects. Energy was a property that defined how much work a system could perform, how much motion it could generate, and how much heat or light it could produce. But even as these early scientists made remarkable progress in understanding how energy behaves, they still hadn't fully answered the most fundamental question. What is energy made of? If it's not a substance that we can touch or see, what exactly is it? Is it a force, a property of matter, or something more abstract like an invisible field that permeates the universe? This is where things begin to get tricky. The deeper we go, the more we realize that the quest for energy's true nature isn't as straightforward as we might hope. Energy is not a single thing. It doesn't have a simple, one-dimensional answer. It manifests in many different forms, each with its own set of rules and behaviors. There's kinetic energy, potential energy, thermal energy, chemical energy, and countless other types. And each of these types of energy behaves in different ways, depending on the system it's part of. For example, when we think of kinetic energy, the energy of motion, we often imagine things like cars speeding down a highway or objects falling from great heights. But kinetic energy can also be found in the vibrations of atoms, the movement of electrons around the nucleus of an atom, and even the stretching of a rubber band. All of these examples involve motion, but they differ in the scale and the forces at play. Kinetic energy in a car is governed by the laws of classical mechanics, while the kinetic energy of particles in a gas is described by the laws of thermodynamics and statistical mechanics. Then there's potential energy, the energy stored in an object because of its position or condition. A rock sitting at the edge of a cliff has potential energy due to its height and the force of gravity acting upon it. But potential energy is not just limited to gravity. It also exists in things like stretch springs, chemical bonds, and even the energy stored in a battery. The concept of potential energy adds another layer of complexity to the idea of energy, making it clear that energy is not a single entity, but a collection of properties that describe how things can change. As we continue to explore the nature of energy, we begin to encounter other questions that further complicate our understanding. For instance, energy can be transferred between objects. When a ball is thrown in the air, the kinetic energy of the throw is converted into potential energy as the ball rises, and then back into kinetic energy as it falls. But what is happening during this process? How does energy change from one form to another, and what determines how much energy can be transferred or converted? Energy transfer is governed by the laws of thermodynamics, which describe the flow of energy between systems and how it changes from one form to another. These laws help us understand why energy flows from hot objects to cold objects, why engines work the way they do, and why it's impossible to build a machine that's 100% efficient. But while the laws of thermodynamics give us a framework for understanding energy's behavior, they don't tell us what energy actually is. They describe how energy behaves, but they don't explain its fundamental nature. So, as we dig deeper into the question of what energy is made of, we find ourselves facing more questions than answers. We know that energy is essential to everything around us, that it's involved in every interaction, every movement, and every change in the universe. But despite centuries of study, energy remains a mysterious force that resists our attempts to fully define it. Is energy just a concept, a tool we use to understand the way things change? Or is it something more, something fundamental to the very structure of the universe? In the quest to understand energy, we've made tremendous strides. We've developed sophisticated tools and equations that allow us to measure, transfer, and convert energy in ways that were once unimaginable. But the deeper we look, the more we realize that energy is a concept that's far more complex than we can fully grasp. It's a part of the fabric of reality itself, a force that shapes the universe in ways we're still working to understand. As we continue to explore the mysteries of energy, we may never fully uncover what it's made of, but the journey itself is what makes the quest so intriguing. Each discovery leads to new questions, each answer opens up more possibilities, and each step forward brings us closer to understanding the forces that drive the universe. And in the end, perhaps that's all we can ask for, an endless journey of exploration, discovery, and wonder. Energy is all around us, shaping everything we see and experience. It's the force behind movement, light, heat, and the countless changes that occur every second in our universe. But energy comes in many forms, each with its own characteristics, rules, and behaviours. The more we understand these different forms, the clearer it becomes that energy is not just a single concept, but a collection of diverse types, each with its own role in the grand tapestry of the cosmos. Understanding these forms is key to grasping the nature of energy itself. The simplest and most intuitive form of energy is kinetic energy, the energy of motion. Kinetic energy is what we observe whenever something is moving, whether it's a car speeding down a highway, a ball thrown through the air, or the molecules vibrating in a hot cup of tea. All of these objects possess kinetic energy. The faster something moves, the more kinetic energy it has. Kinetic energy is tied directly to an object's velocity, its speed in a given direction. But it's not just about how fast something is moving. The mass of the object also plays a significant role. The larger an object is, the more energy it requires to move. That's why a truck moving at 30 miles per hour carries much more kinetic energy than a bicycle travelling at the same speed. But kinetic energy is just one side of the coin. There's another form of energy that's just as fundamental, potential energy. Potential energy is the energy that an object possesses because of its position or state. Unlike kinetic energy, which is associated with motion, potential energy is about an object's potential to do work in the future. Think about a rock sitting at the edge of a cliff. It's not moving, but it has the potential to fall, and when it does, that stored potential energy will be converted into kinetic energy. This is known as gravitational potential energy. The higher the rock is, the more potential energy it has, because it has more room to fall, and therefore can do more work when it hits the ground. Potential energy doesn't just exist in objects that are subject to gravity. It can also be found in other systems. For instance, a compressed spring holds potential energy. When the spring is released, that energy is converted into kinetic energy as the spring expands. Similarly, chemical bonds in molecules also store potential energy. When these bonds are broken, such as when food is digested or fuel is burned, that potential energy is released and often transformed into heat or light. But we're not done yet. There are other forms of energy that may seem a little more abstract but are just as important. One of these is thermal energy. Thermal energy is the energy that comes from the motion of atoms and molecules in a substance. The faster the particles move, the more thermal energy the substance has. This is why heating something up makes it hotter. The heat causes the atoms and molecules to move more quickly, and that increased motion translates into more thermal energy. Thermal energy is also what we sense as heat. When we place our hand near a hot stove, what we're actually feeling is the thermal energy being transferred from the stove to our hand. Thermal energy plays a crucial role in the universe. It drives weather patterns, ocean currents, and even the movement of tectonic plates. It's a central player in processes like combustion and metabolism, and it's involved in every energy conversion we can think of. Whether it's the heat produced by the sun or the warmth of a cup of coffee, thermal energy is at the core of so much of our experience. Another form of energy that we encounter on a daily basis is chemical energy. Chemical energy is stored in the bonds of atoms and molecules. It's released or absorbed during chemical reactions. When we eat food, for example, the chemical energy stored in the food's molecules is transformed into the energy our bodies need to function. Similarly, when we burn fuel, such as gasoline or wood, the chemical energy in those substances is released as heat and light. Chemical energy is everywhere, and it's one of the most common forms of energy we interact with, whether we're fueling a car, cooking dinner, or even breathing. But chemical energy is not the only form of energy that involves invisible forces. Another key form of energy is electromagnetic energy. Electromagnetic energy includes light, radio waves, X-rays, and all the other forms of radiation that travel through space. This form of energy is carried by electromagnetic waves, which are oscillating electric and magnetic fields. The energy carried by these waves depends on their frequency. The higher the frequency of the wave, the more energy it carries. This is why X-rays, which have higher frequencies, are more powerful than radio waves, which have lower frequencies. Light itself is an example of electromagnetic energy, and it's something we encounter constantly. Without electromagnetic energy, we wouldn't have the ability to see or to communicate wirelessly. It's the energy behind our modern technology and much of the world's communication systems. Next, we encounter nuclear energy. Nuclear energy is the energy stored in the nucleus of an atom. This energy is released during nuclear reactions such as fission, splitting an atom, or fusion, combining atoms. Nuclear energy is incredibly powerful, and it's the source of energy for the sun, where hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. On Earth, nuclear energy is harnessed in power plants to generate electricity. While nuclear energy can be highly efficient and potent, it also comes with risks, including radiation hazards and nuclear waste disposal challenges. Each of these forms of energy can be transformed into another form. A classic example of energy transformation is when a power plant converts chemical energy from coal into thermal energy, which is then used to produce steam that turns turbines to generate electricity, which is then transmitted as electromagnetic energy to power our homes. Energy never truly disappears, it simply changes from one form to another. And this idea that energy is always conserved, though it may change forms, is one of the central principles of thermodynamics. While these are some of the primary forms of energy, there are many others that we encounter less frequently, but that are still significant. For example, sound energy is the energy produced by vibrating objects, such as when you speak or when a musical instrument plays. Sound energy is a mechanical wave that travels through a medium, such as air or water, and it's how we hear the world around us. Similarly, elastic energy is the potential energy stored in objects that can be stretched or compressed, like rubber bands or bouncy balls. This type of energy is what allows these objects to return to their original shape after being deformed. But what makes these different forms of energy all part of the same thing? What ties them together, and why are they all considered energy? The answer lies in their ability to do work. Energy, in every form, is a measure of an object's or system's ability to cause change, to move things, to affect the world around it. Whether that change is as large as a rocket launching into space, or as small as a molecule vibrating in a cup of water, energy is always involved. Despite the variety of forms energy can take, the one constant across all of them is that energy is always conserved. This is known as the first law of thermodynamics, the principle that energy cannot be created or destroyed, only transformed. Whether it's the energy of a moving car, the energy stored in a stretched spring, or the energy in a chemical bond, the total amount of energy in a closed system remains constant. It can change forms, but it can never vanish. This fundamental principle is at the heart of how we understand energy in the universe, and it's what allows us to predict how energy will behave in different situations. In the end, the many forms of energy are all expressions of the same underlying concept. Energy is not just a force, nor is it a thing that can be touched or held. It's a way of describing the potential for change, the ability to do work, and the power to shape the world around us. Whether it's kinetic, potential, thermal, chemical, or electromagnetic, each form of energy serves as a reminder that the universe is constantly in motion, constantly changing, and that energy is the force driving it all. Energy is something we experience every day, yet it remains in many ways an invisible force. We don't see energy directly, but we can observe its effects. We can measure its presence in the form of light, movement, heat, and sound. Yet the energy itself remains hidden, like an unseen hand guiding the world around us. This quality of energy, its invisibility, is what makes it so intriguing and, at times, so difficult to fully understand. At its most basic level, energy is not something you can hold in your hand or touch. It's not a tangible substance like air or water, and it doesn't take up space in the way that matter does. Instead, energy is a measure of the ability to do work, to cause changes in matter, to move things, heat things up, or light things up. It's the reason we can walk, why cars move, and why the sun rises every morning. But the reason we often don't recognize energy for what it is because it's not always easy to see or define. Imagine standing in a room where a light bulb is turned on. The light we see is a form of electromagnetic energy, but the energy itself, the light photons, are invisible to the human eye until they hit an object, bounce off, and enter our retinas. We don't see the energy itself, but we can see the result of its interaction with the world. The same can be said for all forms of energy. We don't directly see the kinetic energy of an object in motion, but we can see the object moving. We don't see the thermal energy in a pot of boiling water, but we can feel the heat radiating off of it. Energy makes things happen, but it doesn't always make itself visible in the process. This invisibility is part of what makes energy such a challenging concept to grasp. It's not a substance we can isolate and examine under a microscope. We can't pick up a piece of energy, examine it, and say, "This is energy in its purest form." Instead, we must look at the effects of energy, the motion, the heat, the light, and infer its presence. It's a bit like the wind. You can't see the wind itself, but you can feel it, hear it, and see its effects on the trees and the landscape around you. In much the same way, we experience the effects of energy all around us, even though energy itself remains unseen. One of the most intriguing aspects of energy is that it can take on so many different forms, and yet it's the same underlying force at work in each case. Whether it's the energy that makes the Earth spin on its axis, the energy that powers a computer, or the energy that heats our homes, it's all the same thing, merely taking on different manifestations. But this doesn't mean energy is easy to understand. The more we try to define energy in concrete terms, the more we realize how elusive it is. Take light, for example. Light is a form of energy, specifically electromagnetic energy, and it's one of the few forms of energy that we can perceive directly. But even though we can see light, we can't actually see the photons, which are the particles of light. Instead, we see the result of the photons interacting with the world. This is true of all forms of energy. We experience their effects, but the energy itself remains invisible to our senses. Energy's invisibility is especially apparent when we look at its effects on the microscopic level. When we think of energy, we often think of things we can see, moving objects, light, heat. But on the atomic and subatomic level, energy behaves in ways that are far less intuitive. The movement of electrons, the vibrations of atoms, and the interactions between particles all involve energy, but none of these processes are visible to the naked eye. Instead, we rely on complex instruments and calculations to measure these microscopic forms of energy. Take the example of a molecule of water. At room temperature, the molecules in the water are moving, vibrating and rotating at incredibly high speeds, but we don't see these motions. The energy that drives this movement is thermal energy, but it's invisible to us. We can feel the heat when we touch the water, but we can't see the individual molecules vibrating. This is true for almost all forms of energy at the microscopic level. They exist, they have measurable effects, but we can't directly observe them without the aid of technology. In the same way, energy doesn't have a shape or form we can touch. It doesn't have mass, and it doesn't occupy space in the way that objects or matter do. Energy isn't a thing in itself. It's a concept, a way of describing how systems change and interact. This lack of tangibility is one of the reasons why energy has been so difficult to define. It's not something that fits neatly into our everyday understanding of the world. We can describe energy in terms of its effects, like motion or heat, but the energy itself, the force behind these changes, remains elusive. But the fact that energy is invisible doesn't mean it's not real. Just because we can't see something doesn't mean it doesn't exist. Consider gravity. We can't see gravity, but we know it's there because we observe its effects. Objects fall to the ground, and the planets orbit the sun. Similarly, we can't see energy directly, but we can see its effects in the form of movement, heat, light, and sound. In this way, energy is like gravity. It's an invisible force that shapes the universe, but we experience its influence every moment of our lives. Perhaps one of the most fascinating aspects of energy's invisibility is the way it can be transferred from one object to another, seemingly without any physical contact. Take heat, for example. Heat is a form of thermal energy, and it can be transferred between objects through conduction, convection, and radiation. In conduction, heat flows from one object to another through direct contact, but in radiation, energy can be transferred through empty space. When you feel the warmth of the sun on your skin, the heat is travelling through space as electromagnetic radiation. You can't see the energy itself, but you can feel its effects. Similarly, energy can be transferred between objects through sound waves, light waves, and even through the very air we breathe. This transfer of energy is what allows the universe to work as it does. Without energy, there would be no motion, no heat, no light. Without energy, the world would be a still, dark, and lifeless place. And yet, even though energy is the driving force behind everything in the universe, it remains largely invisible to us. This is part of what makes energy so fascinating. It's a force that shapes the world around us, but we can never quite capture it in its purest form. In some ways, this invisibility makes energy even more powerful. We don't need to see it to know it's there, just as we don't need to see gravity to know that it's keeping us grounded. Energy is a force that operates behind the scenes, making things move, making things change, making the universe function. And while it may be invisible, its effects are undeniable. Energy is everywhere, shaping the universe in ways that we can feel, see, and measure, even if we can never truly grasp its true nature. The first law of thermodynamics is one of the cornerstones of modern physics. It's a simple yet profoundly important principle, one that governs not just the energy systems we encounter in our daily lives, but also the very way the universe functions. In its most basic form, the first law states that energy cannot be created or destroyed. Instead, energy is conserved. It can change forms from one type of energy to another, but the total amount of energy in a closed system remains constant. At first glance, this may seem like a straightforward idea, but when we start to explore its implications, we realize just how powerful and far-reaching it truly is. The first law of thermodynamics tells us that no matter what happens, whether it's a car engine running, a light bulb glowing, or a pot of water heating on the stove, the total amount of energy involved in the process is the same at the beginning and the end. The energy might change from thermal to kinetic or from electrical to mechanical, but the total energy remains the same. This is an incredibly important concept because it helps us understand how energy behaves and why it behaves the way it does. To really grasp the first law, it's helpful to think about energy in terms of systems. A system is simply a collection of matter or objects that are being studied, and it can be as large as the entire universe or as small as a single particle. In a closed system, meaning a system where no energy or matter is exchanged with the outside world, the total energy remains constant. This idea is known as the conservation of energy. So, if energy can't be created or destroyed, how do we see it changing form? Let's take an example. Imagine you have a car engine. The engine burns fuel which releases chemical energy. This chemical energy is then converted into heat, which causes the engine to run and power the car's wheels. The mechanical energy used to turn the wheels is also a form of energy. In this system, we have chemical energy, thermal energy, and mechanical energy, all interacting with each other. However, no energy is lost in the process. The energy that goes into the system as chemical energy is exactly equal to the sum of the mechanical energy that drives the car and the thermal energy that heats the engine. In reality, some energy is often lost as heat, and this heat usually escapes into the surroundings. This is why, when you touch the hood of a running car, it's warm. The heat generated by the engine is a form of energy that's been transformed but hasn't disappeared. It's just been released into the environment. The car engine, while very efficient, cannot operate at 100% efficiency. Some of the energy is inevitably lost as heat due to friction, resistance, and other factors. This is a crucial point to understand, because it's not that the energy has disappeared, it's simply no longer in the form we can easily use. This idea of energy transformation is central to the first law of thermodynamics. In every process, energy can be transferred or transformed, but it cannot simply vanish into thin air. One form of energy might turn into another, thermal energy into mechanical work, chemical energy into electrical energy, and so on. But the total amount of energy in a closed system stays the same. Now think about the Earth itself. In this vast system, the first law of thermodynamics still holds true. The energy that comes from the sun, solar energy, is absorbed by the planet and transformed in a number of ways. Plants use sunlight to make food through photosynthesis, animals eat the plants for energy, and the Earth radiates heat into space. The energy from the sun doesn't vanish. It's transformed and redistributed across the planet in various forms, but the total amount of energy remains constant. This is a grand-scale example of how the first law works on a planetary level, ensuring that energy flows and transforms through different processes while remaining conserved. One of the implications of this law is that it sets a limit on the efficiency of machines and processes. As mentioned before, no machine can be 100% efficient. This is because in any energy conversion, some energy is always converted into heat, which is not useful for doing work. This phenomenon is known as the inefficiency of energy conversion. For example, even the most advanced power plants, which aim to convert thermal energy into electrical energy, will lose some energy to heat in the process. The same goes for the engines that power vehicles or the refrigerators that cool our food. No matter how advanced the technology, there's always some form of energy loss. The first law teaches us that energy is never lost. It's just transformed into a less useful form, like heat, which we often can't use to do work. In daily life, the first law of thermodynamics also shows up when we think about how energy is used and conserved in our homes and businesses. For instance, when you turn on a light, electrical energy flows through the wires and into the light bulb. The electrical energy is then transformed into light and heat. The heat produced is often seen as a waste product, but according to the first law, it's simply another form of energy that has been produced. The total energy input to the system, electricity in this case, is equal to the total energy output, the light you see and the heat that escapes into the room. Another interesting example is when we think about food. Our bodies are constantly converting chemical energy from the food we eat into mechanical energy that allows us to move, grow, and stay alive. When we eat an apple, for example, the body converts the chemical energy stored in the apple's sugars into energy we can use. However, not all of the energy from the apple is converted into mechanical work. Some of it is lost as heat as our bodies break down the food. This is another example of the first law in action. The energy doesn't disappear, but it may be transferred into different forms that we don't always recognize. It's important to note that the first law doesn't tell us anything about how energy flows or the speed at which it changes form. Those questions are tackled by the second law of thermodynamics. The first law is more about the total balance of energy. It tells us that while the forms of energy may change, the total amount of energy in a closed system remains constant. And this conservation of energy is a key to understanding how the universe operates, from the smallest particles to the largest galaxies. This principle of energy conservation is so central to the workings of the universe that it has influenced nearly every field of science. From the study of heat engines in thermodynamics to the understanding of biological systems, from the behavior of atoms in quantum mechanics to the operation of stars and planets in astrophysics, the first law provides a foundation for explaining how energy moves and transforms in the universe. So when you stop to think about it, the first law of thermodynamics is not just a concept confined to the pages of a textbook. It's a universal truth, a law that governs everything from the motion of molecules to the operation of machines and the way the Earth functions as a whole. Energy, though often invisible, is at the heart of everything. It powers the universe, shapes the natural world, and drives the processes of life. And while energy can't be created or destroyed, it will always be changing form, constantly moving, constantly transforming, just as the universe itself is constantly evolving. Energy, in its most fundamental form, begins at the atomic level. When we think of energy, we often picture large systems, cars, machines, the sun. But at the heart of all these processes lies the behavior of the tiniest particles of matter. The atoms and molecules that make up everything in the universe are constantly in motion, and it's this motion, this interaction, that governs the energy at play in all physical processes. The story of energy starts at this small scale, where the rules of physics behave in ways that can seem counterintuitive to our everyday experience. At the atomic level, energy exists in various forms, each playing a crucial role in the way atoms and molecules interact. One of the most important forms of energy at this scale is the energy associated with the motion of particles. Atoms are not stationary, they are in constant motion, vibrating, rotating, and moving in different ways. This motion is governed by thermal energy, which is the energy that comes from the random movement of particles. The faster the particles move, the more thermal energy they possess. This motion, while imperceptible to our senses, is the reason why materials feel hot or cold. When an object is hot, its atoms are vibrating faster. When it's cold, they move more slowly. In fact, the temperature of a substance is directly related to the kinetic energy of its atoms and molecules. Heat energy is simply the transfer of this kinetic energy from one body to another. When you place a hot object near a cooler one, the energy from the fast-moving particles of the hot object is transferred to the slower-moving particles of the cooler object, making it warm up. This transfer continues until both objects are at the same temperature. This concept is a direct consequence of the atomic behavior of energy. Particles are in motion, and that motion translates into energy that can be transferred. But energy at the atomic level doesn't just come from the motion of particles. It also arises from the forces that bind atoms together. Atoms themselves are made up of a nucleus of protons and neutrons, surrounded by a cloud of electrons. The protons in the nucleus carry a positive charge, while the electrons carry a negative charge. This difference in charge creates a force that pulls the electrons toward the nucleus, creating what we call the atomic bond. The energy stored in this bond is called potential energy. It's the energy that holds the atom together and keeps it stable. When atoms bond to form molecules, the energy associated with the bonds between the atoms becomes significant. The energy required to break a bond is called bond energy. and it's a measure of how strongly atoms are held together. This bond energy is a type of potential energy. It is this energy that's released during chemical reactions. When chemical bonds are broken and new bonds are formed, energy is either absorbed or released depending on the nature of the reaction. In exothermic reactions, energy is released, while in endothermic reactions, energy is absorbed. The transfer of energy during these reactions is a key aspect of how energy behaves at the atomic and molecular levels. One of the most important examples of energy at the atomic level is the energy found in the nucleus of an atom, nuclear energy. The nucleus of an atom is held together by the strong nuclear force, which binds protons and neutrons in a dense, compact structure. This force is incredibly powerful, but only operates over very short distances. The energy stored in the nucleus of an atom is what makes nuclear energy so potent. When the nucleus of an atom is split in a process called nuclear fission, or when two atoms fuse together in nuclear fusion, a tremendous amount of energy is released. This energy comes from the strong force holding the nucleus together. The release of this energy is what powers the sun, nuclear reactors, and even nuclear weapons. At the atomic level, energy isn't just about particles moving or bonds being formed. It's also about the way atoms interact with electromagnetic fields. The electrons in an atom occupy discrete energy levels or shells, and when they absorb energy, they can move to higher energy levels. When they fall back to lower energy levels, they release energy in the form of electromagnetic radiation, such as light. This process is at the heart of many phenomena, including the emission of light by atoms in a gas. When an atom absorbs energy, it excites its electrons to a higher energy level, and when those electrons return to their lower energy state, they release energy in the form of light. This is why atoms can produce the colours we see when they are heated or exposed to electrical energy. This principle of energy absorption and emission at the atomic level is also the foundation of technologies like lasers and fluorescent lights. In these devices, atoms or molecules are excited to higher energy levels by an external source of energy, and then they release that energy in a controlled way. The behaviour of electrons within atoms, how they absorb and release energy, is central to many of the technologies that we rely on in our daily lives. At a more fundamental level, the behaviour of energy in atoms and molecules is governed by the laws of quantum mechanics. In classical physics, we think of energy as being continuous, able to take on any value. But in quantum mechanics, energy is quantized. It exists in discrete amounts. This means that energy levels in atoms are not continuous, but come in specific steps. Electrons can only occupy certain energy levels, and the energy they possess corresponds to one of these allowed levels. This quantization of energy is what gives rise to many of the strange and counterintuitive phenomena observed at the atomic and subatomic scales, such as the behaviour of electrons in atoms and the properties of light. The concept of quantized energy is what leads to the strange phenomena that we encounter in the microscopic world. For instance, when we look at light, we see it as a continuous spectrum of colours, ranging from red to violet. However, on a microscopic level, light behaves as though it is made up of discrete packets of energy called photons. These photons are the quantized units of electromagnetic energy. The energy of each photon corresponds to the colour of the light it represents. This idea of energy being quantized leads to a deeper understanding of how energy operates at the atomic and subatomic levels. Energy at the atomic level also plays a central role in the behaviour of matter at high temperatures and pressures. When atoms are subjected to extreme conditions, such as those found in the cores of stars or in the interiors of planets, the energy within the atoms can cause dramatic changes. At very high temperatures, atoms can ionize, meaning that electrons are stripped away from the nucleus, creating ions. This ionization process releases a tremendous amount of energy, and it's the source of the intense heat and light produced by stars. At the other extreme, when atoms are cooled to near absolute zero, their energy levels drop and their particles move more slowly. At these low temperatures, atoms can enter a unique state of matter called a Bose-Einstein condensate. in which they all occupy the same quantum state and behave as a single entity. This state of matter has remarkable properties, such as superfluidity and the ability to conduct electricity with zero resistance. The energy of the atoms in this state is near its minimum, but the effects of this minimal energy can still lead to fascinating phenomena. The atomic scale, while invisible to the naked eye, holds the key to understanding how energy works in the world around us. Whether it's the motion of particles, the formation and breaking of chemical bonds, or the release of energy from atomic nuclei, energy is an intrinsic part of the atomic world. Every chemical reaction, every form of light, every movement in the universe can be traced back to the behavior of atoms and molecules, and it is through these interactions that energy manifests in the ways we observe. As we continue to explore the atomic world, we uncover more of the mystery of energy and its role in the workings of the universe, revealing just how deeply energy is woven into the fabric of reality itself. One of the most perplexing and intriguing aspects of energy is its ability to exist in different forms, often defying the traditional distinctions we make between particles and waves. This duality, where energy behaves both as a particle and as a wave, lies at the heart of quantum mechanics and represents a major shift in our understanding of the universe. At the atomic and subatomic level, energy is not confined to a single, easily definable behavior. Instead, it can exhibit characteristics of both particles and waves, depending on how it is observed. This strange phenomenon is known as the particle-wave duality of energy, and it challenges the very foundation of how we think about the physical world. To understand this duality, we first need to revisit some basics. In classical physics, we typically think of particles and waves as distinct concepts. Particles are tiny, localized pieces of matter, like the electrons orbiting an atom or the atoms themselves. Waves, on the other hand, are disturbances or oscillations that travel through a medium, such as sound waves traveling through air or light waves traveling through space. Waves are not localized in space, they spread out, and their energy is distributed over a wide area. In classical mechanics, energy would either be associated with a particle or a wave, but not both at the same time. However, quantum mechanics, the branch of physics that deals with the very small, has shattered these distinctions. The discovery that energy behaves both as a particle and as a wave came about in the early 20th century, with the work of scientists like Albert Einstein, Niels Bohr, and Louis de Broglie. These scientists began to realize that the behavior of subatomic particles, like electrons, protons, and photons, did not always follow the rules of classical physics. Instead, these particles exhibited behaviors that were more consistent with waves. One of the key experiments that helped reveal this particle-wave duality was the famous double-slit experiment. In this experiment, a beam of particles, such as electrons, was directed at a screen with two slits in it. When the electrons were sent through the slits, they created an interference pattern on the screen, just as light waves would. This pattern is characteristic of waves, not particles. If electrons were behaving like particles, we would expect them to pass through one slit or the other and create two distinct patterns on the screen. But the interference pattern, with its alternating dark and light bands, showed that the electrons were behaving like waves, spreading out and interfering with each other. However, when scientists attempted to observe which slit the electrons passed through, effectively measuring their position, the interference pattern disappeared. Instead, the electrons behaved like particles, passing through one slit or the other without any interference. This strange behavior, where electrons acted like both particles and waves depending on whether or not they were being observed, was a key breakthrough in quantum mechanics. It suggested that the very act of observation, of measurement, was enough to determine how energy would behave. This duality isn't limited to electrons, it applies to all forms of energy. Photons, the particles of light, also exhibit both particle and wave characteristics. In some experiments, light behaves like a stream of particles, each carrying energy, while in other experiments, light behaves like a wave, spreading out and forming interference patterns. The wave nature of light is most clearly seen in phenomena like diffraction, where light waves bend around obstacles, and interference, where two waves overlap and combine to form a new pattern. But light's particle nature is evident when it interacts with matter in certain ways, like in the photoelectric effect, where light strikes a metal surface and knocks electrons loose. This particle-wave duality challenges our classical understanding of energy and matter. In the world of everyday objects, we can typically think of energy as either a particle or a wave, depending on the situation. But at the quantum level, energy doesn't fit neatly into either category. Instead, it exists in a state that is both particle and wave at the same time. This behavior is described by the concept of wave-particle duality, a fundamental principle of quantum mechanics. Wave-particle duality is not just an oddity of light or electrons, it applies to all particles with mass, including atoms and molecules. The larger the object, the less pronounced the wave-like behavior becomes, because the particle nature dominates. But for very small particles, the wave-like properties are significant and cannot be ignored. This duality is described mathematically by a quantity known as the de Broglie wavelength, which gives the wavelength associated with a moving particle. The de Broglie wavelength is inversely related to the particle's momentum. The greater the momentum of the particle, the shorter its wavelength, and the less likely it is to exhibit wave-like behavior. What this means is that at the atomic and subatomic scales, energy cannot be fully understood using classical physics alone. Classical physics assumes that particles and waves are separate entities, each governed by different rules. But quantum mechanics tells us that at small scales, energy can behave like both a particle and a wave, and this behavior is governed by probabilities, not certainties. This is a key feature of quantum theory. Particles don't have definite positions and velocities until they are measured. Instead, they exist in a range of possible states, with each state having a certain probability of being observed. This probabilistic nature of energy is encapsulated in the concept of the wave function, which describes the probabilities of where a particle might be and what energy it might have. The wave function is a mathematical expression that gives us a complete description of the possible states of a quantum system. When a measurement is made, the wave function collapses to a single outcome. Until the measurement is made, the system exists in a superposition of possible states, essentially a mix of all possible locations and energies. The wave-particle duality of energy has profound implications for how we understand the universe. It forces us to abandon our classical intuition, where particles and waves are separate and distinct. Instead, quantum mechanics shows us that energy, at its most fundamental level, is not one or the other, it's both. This realization has changed the way we think about everything, from the behavior of light to the fundamental nature of matter itself. One of the most famous manifestations of wave-particle duality is the uncertainty principle, introduced by Werner Heisenberg. This principle states that it is impossible to simultaneously know both the position and the momentum of a particle with absolute certainty. The more precisely we measure one of these quantities, the less precisely we can know the other. This is not a limitation of our measurement tools, it's a fundamental feature of the quantum world. The very act of measurement disturbs the system, and the system doesn't have definite properties until it's observed. This uncertainty is a direct consequence of the wave-particle duality of energy. Wave-particle duality has far-reaching consequences beyond just our theoretical understanding of the universe. It forms the basis for many modern technologies, such as semiconductors, lasers, and quantum computers. These technologies rely on the principles of quantum mechanics and the dual nature of energy to work. For instance, in semiconductors, the behavior of electrons as both particles and waves allows for the creation of the tiny, efficient devices that power our electronics. In quantum computers, the superposition of quantum states allows for computations that are exponentially faster than classical computers for certain types of problems. Understanding the particle-wave duality of energy is not just an academic exercise. It has real-world applications that are shaping the future of technology and science. But it also forces us to reconsider our view of the universe. Energy, at the most fundamental level, is not something simple. It's a complex, multifaceted phenomenon that defies our classical intuitions. Whether it's light, electrons, or atoms, energy is constantly shifting between its particle and wave forms, and this behavior is central to how the universe works at the smallest scales. The wave-particle duality is one of the most striking features of quantum mechanics, and it reveals just how different the quantum world is from the one we experience in our daily lives. At the atomic and subatomic levels, energy doesn't behave according to the simple rules of classical physics. Instead, it behaves according to the strange, probabilistic principles of quantum mechanics. This behavior is not just a curiosity, it's a fundamental part of the structure of reality itself. Energy at the quantum level behaves in ways that defy the expectations set by classical physics. The quantum nature of energy is one of the most profound and perplexing aspects of modern science. Unlike classical mechanics, which deals with macroscopic objects and predictable outcomes, quantum mechanics reveals a world where energy is governed by uncertainty, probability, and wave-particle duality. To understand the quantum nature of energy, we need to delve into the strange and fascinating principles that govern the behavior of particles and energy at the smallest scales. At the heart of quantum mechanics lies the concept that energy is quantized. This means that energy doesn't exist in a continuous flow, but rather in discrete units, or quanta. Just as matter is made up of atoms and molecules, energy is made up of these indivisible packets. The idea that energy comes in discrete packets was first proposed by Max Planck in the early 20th century, when he was studying the radiation emitted by heated objects. Planck introduced the concept of the quantum, a small unit of energy, to explain the observed pattern of radiation. He proposed that energy could only be absorbed or emitted in fixed amounts, rather than in any arbitrary quantity. This idea was further developed by Albert Einstein, who applied it to light. In 1905, Einstein proposed that light itself is made up of discrete packets of energy, which he called photons. According to this theory, light, which had been traditionally thought of as a wave, also had properties of particles. This duality, where light behaves as both a wave and a particle, became a cornerstone of quantum theory and introduced the concept of energy being quantized. The energy of each photon is directly proportional to the frequency of the light, meaning that higher frequency light, like blue or violet, carries more energy per photon than lower frequency light, like red or infrared. The notion that energy is quantized was revolutionary. It shattered the classical view that energy could take on any value, instead suggesting that energy is inherently discrete at the smallest scales. This quantization of energy is not limited to light. It applies to all forms of energy at the atomic and subatomic levels. Electrons, for example, occupy discrete energy levels within an atom. They cannot exist in between these energy levels, and they can only absorb or emit energy in specific amounts when they move between levels. This quantization of energy levels is what gives atoms their unique properties, such as their ability to absorb and emit light at specific wavelengths. The idea of quantized energy is encapsulated in the mathematical framework of quantum mechanics, where the energy of a system is described by a wave function. The wave function is a mathematical function that provides information about the probabilities of a particle's position and energy. It's a way of describing a system's state in terms of probabilities rather than definite values. The wave function itself is not something that can be directly observed, but it gives rise to observable quantities such as energy levels when it's measured or collapsed. One of the most important consequences of this quantum nature of energy is the phenomenon of superposition. In quantum mechanics, particles can exist in multiple states at once, a situation known as superposition. For example, an electron in an atom can exist in multiple energy states simultaneously, each with a certain probability. When a measurement is made, however, the superposition collapses and the electron assumes a single energy state. This is fundamentally different from classical physics, where objects are always in one state at any given time. In the quantum world, things are uncertain until they are observed, and energy is no exception. The uncertainty principle, formulated by Werner Heisenberg, is another key concept that arises from the quantum nature of energy. The uncertainty principle states that it's impossible to know both the exact position and the exact momentum, or velocity, of a particle simultaneously with absolute certainty. The more precisely one of these quantities is measured, the less precisely the other can be known. This is not due to limitations in measurement technology, but rather a fundamental feature of the quantum world. The uncertainty principle reflects the inherent indeterminacy of energy and particles at the quantum level. This uncertainty extends to the energy of a system as well. The energy of a particle is not fixed until it is measured. Instead, the particle exists in a range of possible energy states, each with a certain probability. The energy of a quantum system is not deterministic. It's probabilistic, governed by the wave function, which provides the likelihood of finding the system in a particular energy state when it is observed. This means that, at the quantum level, energy isn't just a value we can calculate. It's a spectrum of possibilities, each with a different probability of occurring. Quantum mechanics also introduces the concept of quantum fluctuations, which further highlight the probabilistic nature of energy. In the vacuum of empty space, energy isn't truly absent. Instead, it fluctuates, with particles and antiparticles spontaneously appearing and annihilating each other. These fluctuations are temporary, and the energy involved is typically very small, but they demonstrate that even in seemingly empty space, energy is constantly in motion. This is a manifestation of the quantum nature of energy, an ever-changing probabilistic field that underlies all physical phenomena. One of the most striking examples of quantum energy is the phenomenon of quantum tunneling. Quantum tunneling occurs when particles, such as electrons, pass through barriers that would be insurmountable according to classical physics. This happens because of the wave-like nature of particles at the quantum level. Instead of being confined to a specific location, the particle's wave function spreads out, allowing it to tunnel through a barrier even if it doesn't have enough energy to overcome it in a classical sense. This behavior is essential in many processes, including nuclear fusion in stars and the functioning of certain types of semiconductors and transistors used in modern electronics. The concept of energy in quantum mechanics is also closely linked to the idea of quantized fields. In quantum field theory, energy is seen as the result of fluctuations in fields that permeate space. These fields, such as the electromagnetic field, are quantized, meaning that the energy they carry exists in discrete amounts. The interactions between these fields and particles give rise to the energy that we observe in the universe. Quantum field theory provides a unified framework for understanding the quantum nature of energy, and is one of the most successful theories in modern physics. At the quantum level, energy is not a continuous flow, but a collection of discrete units, constantly fluctuating and existing in a state of uncertainty. It's a world where particles can behave as waves, where energy is not fixed but probabilistic, and where the very act of observation can influence the outcome of a process. This quantum nature of energy has led to groundbreaking discoveries and has fundamentally changed our understanding of the universe. From the development of quantum technologies, such as lasers and quantum computers, to the understanding of the behavior of atoms and molecules, the quantum nature of energy is a key to unlocking the mysteries of the physical world. Understanding the quantum nature of energy forces us to let go of the deterministic classical view of the universe and embrace a new reality, one that is governed by probabilities, uncertainties, and the strange behaviour of energy at the smallest scales. It's a world that challenges our intuition and invites us to think in new and profound ways about the very nature of reality. The question of where energy comes from is deeply tied to the origins of the universe itself. Understanding the birth of energy is not just a scientific inquiry. It's a journey into the very beginning of everything we know. To explore this, we must look to the earliest moments of the universe, when energy was first unleashed in what we now call the Big Bang. This event, nearly 13.8 billion years ago, marks the point at which the universe, and all the energy within it, began its journey of expansion, transformation, and evolution. Before the Big Bang, there was no space, no time, and certainly no matter or energy as we understand them. The universe was, for all practical purposes, a singularity, a point of infinite density where the laws of physics as we know them break down. In this state, it is believed that all of the energy in the universe was concentrated in a single point. The concept of energy itself doesn't have meaning in the traditional sense before the Big Bang, as everything that would eventually give rise to the universe, including energy, was compressed into an extremely hot, dense, and incredibly small space. But as the universe began to expand, so did the energy it contained. The moment of the Big Bang was not an explosion in space, it was an explosion of space itself. Space, time, and all the energy in the universe began expanding rapidly in what scientists call cosmic inflation. This rapid expansion, happening in a fraction of a second, spread out the energy in the universe. But during these early moments, the energy wasn't in the familiar forms we encounter today. Instead, the energy was in the form of radiation, extremely hot and dense with particles of light, or photons, racing through the universe at nearly the speed of light. The energy in the early universe was primarily electromagnetic radiation, as the temperature of the universe was too high for matter as we know it to exist. As the universe continued to expand and cool, energy began to transition from its pure radiative form into the first particles of matter. This transition is a pivotal moment in the birth of energy. The energy that existed in the very early universe, although primarily in the form of radiation, began to condense into matter. This process is explained by Einstein's famous equation E=mc², which tells us that energy and matter are interchangeable. As the universe cooled, the high-energy photons began to decay into particles of matter. This was the moment when matter and energy began to separate in a more recognizable form. As particles began to form, the energy contained in those particles manifested as what we now know as the building blocks of matter, quarks, leptons, and the very first atoms. In this early universe, quarks combined to form protons and neutrons, while electrons existed in a hot, dense plasma that made up the early universe. The energy released during these processes wasn't just confined to the particles themselves, it also existed in the interactions between them. These interactions were intense, as the universe was still in a state of rapid expansion and cooling, creating a dense and energetic environment in which energy was constantly being transferred between particles. As the universe continued to expand and cool, the fundamental forces that govern the universe began to separate from one another. Initially, the electromagnetic force, weak force, and strong force were unified as a single force in what's known as the Grand Unification Epoch. But as the temperature dropped, these forces began to take on distinct identities, giving rise to the forces that we are familiar with today. The energy that was once unified began to disperse into different forms. Some of it went into forming matter, while some remained in the form of radiation. It was during this process that the familiar forms of energy, such as the kinetic energy of particles, the potential energy of matter, and the thermal energy of radiation, began to take on their present forms. The birth of energy is closely tied to the evolution of the universe itself. As the universe continued to cool and expand, matter began to coalesce into the first atoms, Hydrogen, the simplest element, formed from protons and electrons, and over millions of years these atoms began to clump together under the force of gravity, eventually forming stars. Inside these stars, nuclear fusion began, a process in which atomic nuclei fused to form heavier elements, releasing vast amounts of energy in the process. This is one of the most significant stages in the birth of energy as we understand it, because it was through the fusion of hydrogen and helium that the energy of stars, energy that powers everything from the formation of galaxies to the very conditions that allow life to exist, was released. Stars are the engines of energy in the universe. Through nuclear fusion, they convert mass into energy, following the laws of the first law of thermodynamics. The energy produced by stars, heat, light, and radiation, has played a critical role in shaping the universe as we know it. As stars lived and died, they scattered their energy and matter throughout the cosmos. The remnants of these stars, in the form of stardust and heavier elements, contributed to the formation of new stars, planets, and galaxies, perpetuating the cycle of energy release and transformation. At the same time, the energy that permeated the early universe also played a significant role in shaping the forces and structures that we observe in the universe today. As the universe expanded, the energy contained within it spread out, but it also took on different forms, influenced by the expanding space itself. The energy that existed in the earliest moments of the universe has been carried forward into the present, shaping the universe's continued evolution. But what is the origin of this energy? The very beginning of energy's existence is intimately tied to the Big Bang itself. The total energy of the universe, while unquantifiable in its entirety, can be thought of as the energy that emerged from the initial singularity, the point at which all energy was concentrated before the Big Bang. This energy wasn't created in the sense that we often think of creation. It was an inherent property of the universe itself, a property that, through the expansion of the cosmos, transformed and became the energy we observe today in the forms of matter, radiation, and the fundamental forces that govern our universe. The birth of energy is both a physical and a philosophical question. It's tied to the creation of the universe, the formation of matter, and the evolution of the forces that shape the cosmos. Energy is not just something we observe in our daily lives. It is something that emerged from the very fabric of the universe itself. It is as old as the universe, and as fundamental to its existence as space and time. The energy that drives stars, fuels galaxies, and powers the forces of nature began at the moment of creation and continues to evolve and transform just as the universe does. While we may never fully understand the exact origin of energy, we do know that its birth is inseparable from the birth of the universe. The two are forever intertwined, with energy continuously transforming and evolving, shaping the universe from its earliest moments to the present day. And as the universe continues to expand, so too will the energy within it, constantly shifting and adapting to the ever-changing cosmos. The relationship between matter and energy is one of the most fundamental concepts in physics. These two entities are intimately linked, and understanding their interplay is key to understanding how the universe works. Matter and energy are not separate, independent entities. They are two sides of the same coin. In fact, one of the most profound discoveries in physics, made by Albert Einstein, is that matter and energy are interchangeable. This idea, encapsulated in his famous equation E=mc², reveals a deep connection between the two and has reshaped our entire understanding of the universe. At its core, Einstein's equation tells us that energy and mass are two different manifestations of the same thing. Mass, which is the property of matter that gives it weight and inertia, can be converted into energy, and energy can be converted into mass. This is a revolutionary idea, as it means that mass, which we once thought of as a property of matter, is actually a form of energy. In simple terms, energy is what gives matter its substance, and matter is simply condensed energy. To understand this relationship, consider an example. nuclear reactions. In the Sun, nuclear fusion occurs when hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the process. This energy is a direct result of the conversion of mass into energy. When two hydrogen nuclei combine to form a helium nucleus, the mass of the resulting helium atom is slightly less than the total mass of the original hydrogen atoms. This missing mass has been converted into energy, which is released as light and heat. This process powers the Sun, providing the energy that sustains life on Earth. This interplay of matter and energy is not limited to the Sun. It occurs in many different processes, both natural and man-made. In nuclear reactors, for example, the process of nuclear fission involves the splitting of heavy atomic nuclei, such as uranium or plutonium. When these nuclei split, they release a significant amount of energy. The mass of the resulting smaller nuclei is slightly less than the original heavy nucleus, and this difference in mass is converted into energy. This is the principle that powers nuclear power plants, where energy is harnessed by the controlled splitting of atoms. The relationship between matter and energy is not just important in the context of nuclear reactions, it is present in every interaction in the universe. When an object moves, for example, it possesses kinetic energy. The faster the object moves, the more kinetic energy it has. Similarly, when an object is lifted to a certain height, it possesses potential energy. This potential energy is a result of the object's position in a gravitational field. As we observe the motion and position of objects, we are also observing the energy that is tied to their mass. In a sense, the mass of an object determines how much energy it can potentially store or release. One of the most striking examples of the interplay between matter and energy occurs in particle physics. At the subatomic level, particles are constantly interacting with each other, exchanging energy in the form of forces. These forces, such as the electromagnetic force, the strong nuclear force, and the weak nuclear force, govern the behavior of particles and determine the properties of matter. These forces are themselves manifestations of energy. For example, when an electron interacts with a photon of light, it can absorb energy from the photon, causing the electron to move to a higher energy level. Similarly, when particles collide, their energy can be converted into new particles, creating matter from energy. This idea of matter and energy being interchangeable is not limited to large-scale phenomena like nuclear reactions or particle collisions. It also applies to everyday processes. For instance, when we burn fuel, such as gasoline in an engine or wood in a fireplace, we are releasing the chemical energy stored in the bonds between atoms. This energy is converted into heat, which can be used to do work such as powering a car or heating a home. In these processes, the matter in the fuel is transformed into energy in the form of heat and light, and the total energy in the system remains conserved, as described by the first law of thermodynamics. But the interplay of matter and energy is not always as straightforward as the conversion of mass into energy, or the release of energy from matter. At the quantum level, this relationship becomes even more complex and fascinating. In the quantum world, particles are not simply points of mass, they also exhibit wave-like properties. This wave-particle duality means that particles can exist in multiple states at once, and their energy is not fixed until it is measured. This probabilistic nature of energy in quantum systems means that matter itself is not as solid and predictable as we might think. Instead, matter exists as a combination of probabilities, and the energy associated with it is equally uncertain. This uncertainty is captured by the Heisenberg uncertainty principle, which states that it is impossible to know both the exact position and the exact momentum of a particle simultaneously with perfect precision. The more accurately we know one property, the less precisely we can know the other. This uncertainty in the behavior of matter and energy at the quantum level has profound implications for our understanding of the universe. It means that, at the smallest scales, the relationship between matter and energy is not fixed but probabilistic. with energy existing in a range of possible states until it is observed or measured. The interplay of matter and energy also comes into play in the theory of relativity. According to Einstein's general theory of relativity, the presence of matter and energy can warp space-time itself. The more mass or energy an object has, the more it bends the fabric of space and time around it. This bending of space-time is what we experience as gravity. The Earth's mass warps the fabric of space-time, creating a gravitational field that attracts objects toward it. Similarly, light, which is a form of energy, is also affected by gravity. In fact, light travels more slowly when it passes through regions of space with strong gravitational fields, a phenomenon known as gravitational time dilation. This connection between matter, energy, and space-time is one of the most striking predictions of Einstein's theory. It tells us that matter and energy are not just abstract quantities, but are intimately tied to the structure of the universe itself. Matter and energy do not exist in isolation. They are part of the very fabric of space-time, shaping the way the universe evolves and behaves. The interplay of matter and energy is also central to the field of cosmology, which studies the structure and evolution of the universe. The Big Bang theory, which describes the origin of the universe, tells us that at the very beginning, the universe was incredibly hot and dense, with all the matter and energy of the cosmos concentrated in a single point. As the universe expanded and cooled, energy and matter began to take on different forms. Stars formed, galaxies came into existence, and the universe as we know it began to evolve. Throughout this process, energy and matter have continued to interact, giving rise to the universe's vast complexity and the variety of phenomena we observe today. In the modern world, we see the interplay of matter and energy in countless technologies. In electricity generation, for example, we convert mechanical energy into electrical energy using turbines and generators. In computers, energy is used to power circuits and perform calculations. In telecommunications, electromagnetic energy is transmitted across vast distances to carry information. In all of these technologies, the interplay between matter and energy is what makes it possible for us to do work, communicate, and power the modern world. The relationship between matter and energy is not just a theoretical concept, it is the very foundation of the universe. From the smallest particles to the largest galaxies, from the birth of stars to the energy that powers our homes, matter and energy are constantly interacting and transforming. This interplay shapes everything we know, from the behavior of atoms to the structure of the cosmos. And as we continue to explore the universe, we will undoubtedly discover even more ways in which matter and energy work together to create the reality we experience. Energy and forces are fundamental to our understanding of the physical world. Every interaction, every motion, and every transformation of matter is the result of energy being exchanged between systems, and it's the forces acting between those systems that govern how energy flows and changes. While energy is a measure of the ability to do work, forces are the agents that enable work to be done. Forces cause objects to move, change direction, or undergo transformations, and energy is the result of these changes. The relationship between energy and forces is central to nearly every process in the universe, from the smallest interactions between atoms to the grand motions of planets and galaxies. To begin, let's take a look at the fundamental forces in the universe. In classical physics, we usually discuss four fundamental forces: gravitational force, electromagnetic force, weak nuclear force, and strong nuclear force. Each of these forces plays a different role in the way matter and energy interact. Gravitational force, the force of attraction between masses, is the force that governs the motion of planets, stars, and galaxies. Gravity is the force that causes an apple to fall to the ground, the moon to orbit the Earth, and the Earth to orbit the Sun. The energy associated with gravity is potential energy, often called gravitational potential energy. This energy is related to an object's position within a gravitational field. The higher an object is above the ground, the more potential energy it has. When the object falls, this potential energy is converted into kinetic energy, the energy of motion. In this way, gravitational force is responsible for converting potential energy into kinetic energy and vice versa. Electromagnetic force is the force responsible for the interactions between charged particles, such as electrons and protons. This force is responsible for a wide range of phenomena, from the attraction between opposite charges to the repulsion between like charges. Electromagnetic forces govern everything from the behavior of atoms and molecules to the way light travels through space. The energy associated with electromagnetic force is electromagnetic energy, which can be in the form of light, radio waves, X-rays, and other types of radiation. Electromagnetic energy is also what powers much of modern technology, including computers, televisions, and telecommunication systems. The weak nuclear force and the strong nuclear force are the forces responsible for the interactions within atomic nuclei. These forces act at extremely small distances inside atoms and govern the behavior of subatomic particles like protons and neutrons. The strong nuclear force holds protons and neutrons together within the nucleus, while the weak nuclear force is responsible for certain types of particle decay, such as beta decay. Both of these forces involve the conversion of mass into energy, as seen in nuclear reactions. For example, in nuclear fusion, the energy released comes from the conversion of mass to energy, as hydrogen atoms fuse to form helium. This process powers the sun and provides us with the energy we observe as sunlight. Now let's explore how forces are related to energy in more detail. Forces cause changes in the state of motion of objects, and energy is the measure of those changes. When a force is applied to an object, it does work on that object. The work done by a force is the transfer of energy from one system to another, and it is given by the product of the force and the displacement of the object in the direction of the force. For example, if you push a box across the floor, you are applying a force that causes the box to move. The work you do on the box is transferred into kinetic energy, the energy of motion. This relationship between force and energy is captured in the work energy theorem, which states that the work done on an object is equal to the change in the object's kinetic energy. This theorem is a direct consequence of Newton's second law of motion, which tells us that the force applied to an object is proportional to its mass and the acceleration of the object. The force causes the object to accelerate, and the work done results in a change in the object's kinetic energy. Forces are not only responsible for changes in motion, but also for changes in the energy stored in systems. For instance, in a spring, when a force is applied to compress or stretch the spring, potential energy is stored in the system. The energy required to compress or stretch the spring is directly related to the force applied, and this stored energy can be released when the spring is allowed to return to its original shape. Similarly, forces can change the internal energy of systems, such as the energy stored in chemical bonds or the energy in the form of heat. In a chemical reaction, for example, the forces between atoms and molecules are rearranged, releasing or absorbing energy. The relationship between forces and energy is also crucial in understanding the transfer of energy. Energy is often transferred from one object to another through the application of forces. This can occur in a variety of ways, such as through mechanical work, heat transfer, or the flow of electromagnetic radiation. For instance, when you lift an object against gravity, you're doing work on the object, transferring energy from your muscles into the object in the form of gravitational potential energy. When you touch a hot object, heat is transferred from the object to your skin, raising the temperature of your body. In both cases, energy is being transferred as a result of forces acting on the system. One of the key concepts in understanding the interplay of energy and forces is the law of conservation of energy, which states that energy cannot be created or destroyed, only transformed from one form to another. This law applies to all processes involving forces and energy. For example, When a car brakes, the kinetic energy of the car is converted into heat energy by the friction between the brake pads and the wheels. The total amount of energy in the system is conserved, but the form of energy has changed. Similarly, in a roller coaster, the potential energy at the top of the track is converted into kinetic energy as the coaster car descends, and then back into potential energy as it climbs the next hill. Throughout this process, the total energy in the system remains constant, but the energy is continually transformed between different forms. In more complex systems, energy can also be transferred through waves. For instance, electromagnetic waves, such as light and radio waves, carry energy across vast distances. The energy of these waves is a result of the electromagnetic force, which causes the oscillating electric and magnetic fields to propagate through space. The energy carried by these waves can be absorbed by matter, as seen when sunlight warms the Earth, or when radio waves are used to transmit information. In these cases, forces act on particles to transfer energy through the medium of the wave. The interplay of energy and forces is also critical in understanding how energy flows in larger systems, such as ecosystems or the Earth's climate. In these systems, energy is constantly being transferred and transformed, often in complex ways. For example, in the Earth's atmosphere, energy from the sun is absorbed by the surface, where it's converted into heat energy. This heat is then transferred through the atmosphere by convection, radiation, and conduction, driving weather patterns and influencing the global climate. Forces such as gravity, air pressure, and the Coriolis effect play a role in shaping the movement of energy within these systems. In the larger context of the universe, the interplay of forces and energy governs the formation of galaxies, the motion of celestial bodies, and the life cycles of stars. The gravitational force causes matter to clump together, forming stars and galaxies, while the energy produced by nuclear fusion in stars powers the creation of new elements and drives the processes that sustain life on Earth. The interactions of energy and forces on a cosmic scale shape the structure of the universe and determine its evolution over time. The study of energy and forces is fundamental to all of physics, from the smallest particles to the largest cosmic structures. Whether it's the forces that govern the motion of planets, the energy that powers chemical reactions, or the electromagnetic energy that makes modern technology possible, the interplay of energy and forces is at the heart of every physical process. Understanding this relationship not only helps us explain the world around us, but also unlocks the potential for new technologies and deeper insights into the workings of the universe. Energy transfer is one of the most fundamental processes in nature. It occurs whenever energy moves from one system or object to another, and understanding how energy is transferred is essential for grasping the behavior of physical systems. Energy doesn't stay in one place. It's constantly being transferred between objects, changing forms, and creating the dynamic world we experience. Whether it's heat flowing from a hot cup of coffee to the surrounding air, or the mechanical energy from a moving car being transferred to the wheels, energy transfer is a part of everything around us. In fact, all the processes we see in nature, from the functioning of machines to the behavior of stars, are essentially energy transfer in one form or another. Energy can be transferred in many different ways, and the mode of transfer depends on the nature of the system involved and the form of energy being transferred. The three main mechanisms of energy transfer are conduction, convection, and radiation. Each of these methods plays a crucial role in different processes, whether in everyday life or in more complex systems like the weather or the operation of engines. Conduction is the transfer of energy through direct contact between objects. It occurs when particles of a material collide with one another, transferring their energy in the process. This method of energy transfer is most commonly seen with heat, but it can also apply to other forms of energy, such as sound or electricity. When a hot object, such as a metal rod, is placed in contact with a cooler object, the molecules in the hot object vibrate more rapidly than those in the cooler object. As the molecules in the hot object collide with those in the cooler object, they transfer some of their kinetic energy to the cooler molecules, causing the cooler object to heat up. This is how heat travels from the stove to a pot or from a heating pad to your body. The rate of conduction depends on the properties of the materials involved, such as their thermal conductivity. Materials like metals, which have free-moving electrons, conduct heat very efficiently, while insulating materials like wood or rubber conduct heat much more slowly. An important concept in conduction is the idea of thermal equilibrium. When two objects are in thermal contact, energy will transfer between them until they reach the same temperature. At this point, energy transfer ceases because the objects are at the same temperature, and no more heat flows between them. This process of conduction plays a central role in everything from cooking to the heating of buildings to the cooling of electronics. Convection is the transfer of heat energy through the movement of a fluid, liquids, or gases. Unlike conduction, which occurs through direct contact, convection relies on the movement of particles within the fluid to carry energy from one place to another. This process is what drives weather patterns, ocean currents, and even the operation of heat systems in homes. In convection, hot areas of a fluid become less dense and rise, while cooler areas become more dense and sink. This movement creates a cycle, or a convection current, that allows energy to be transferred through the fluid. A simple example of convection can be seen when heating a pot of water. As the water at the bottom of the pot heats up, it becomes less dense and rises to the top, while cooler water from the top sinks to replace it. This constant circulation of water allows heat to be distributed throughout the pot. Convection is also responsible for the circulation of air in the atmosphere, which drives weather systems like wind, storms, and ocean currents. In the Earth's atmosphere, convection currents are responsible for the formation of clouds and the distribution of heat across the planet. The sun heats the Earth's surface, warming the air near the ground. As this warm air rises, cooler air from higher altitudes moves in to take its place, creating the wind patterns we experience. In larger systems, such as the Earth's oceans, convection plays a role in regulating the planet's climate by transporting warm water from the equator toward the poles and cold water from the poles toward the equator. Radiation is the transfer of energy through electromagnetic waves, which can travel through a vacuum, empty space. Unlike conduction and convection, which require a medium like air or water to transfer energy, radiation can occur through the vacuum of space. This is how the sun's energy reaches the Earth, despite the vast emptiness of space between them. Radiation occurs through the emission of electromagnetic waves, including visible light, infrared radiation, ultraviolet light, and other types of radiation. These waves carry energy, and when they interact with matter, they can be absorbed, reflected, or transmitted. For example, when sunlight hits the Earth, it transfers energy in the form of visible light and heat. The surface of the Earth absorbs this radiation, warming up the planet and making life possible. Similarly, the heat we feel from a campfire or a radiator is also a form of radiant energy, which travels through the air in the form of infrared radiation. One of the key aspects of radiation is that it doesn't require a medium to transfer energy. This is why radiation is the primary mode of energy transfer from the sun to the Earth. In fact, all objects emit radiation depending on their temperature. Hotter objects like the sun emit radiation at higher frequencies such as ultraviolet light, while cooler objects like the Earth emit radiation at lower frequencies such as infrared light. The balance of radiation absorbed and emitted by the Earth is crucial for maintaining the planet's temperature and supporting life. While conduction, convection, and radiation are the primary mechanisms by which energy is transferred, these processes often work together in complex systems. For instance, in the atmosphere, heat is transferred from the sun to the Earth through radiation, but the heat is then distributed around the globe through convection currents in the air and oceans. Similarly, in the human body, heat produced by cellular processes is transferred through conduction to the surrounding tissues, while convection helps regulate body temperature by allowing heat to escape through the skin. In machines and engines, energy transfer is a key part of their functioning. For example, in a steam engine, energy is transferred from the heat source, such as burning coal, to water, converting water into steam. The steam then moves through pipes and turns a turbine, converting thermal energy into mechanical energy. In this system, energy is transferred through both conduction from the heat source to the water and mechanical work from the steam to the turbine. In electrical circuits, energy is transferred through the movement of electrons from the power source to the devices being powered. Another important example is in the transfer of energy in electrical systems. When we generate electricity at a power plant, mechanical energy is often used to turn a turbine, which drives a generator that produces electrical energy. The electrical energy is then transferred through power lines and distributed to homes and businesses, where it can be used to power lights, appliances, and devices. In these systems, energy transfer occurs through both mechanical and electrical means, and it's essential that the energy be efficiently transferred to reduce losses along the way. Energy transfer is crucial to the functioning of ecosystems. Plants absorb energy from the sun through photosynthesis, converting sunlight into chemical energy that they store as glucose. Herbivores then consume plants, transferring that energy into their own bodies, and carnivores in turn consume herbivores. This transfer of energy from one organism to another is the foundation of food webs and ecosystems sustaining life on Earth. Energy flows through the ecosystem, from the sun to plants, from plants to herbivores, and from herbivores to carnivores, with each step transferring energy and creating the dynamics of life. In the Earth's climate system, energy transfer between the atmosphere, oceans and land masses drives weather patterns, ocean currents, and the planet's temperature. Heat from the sun is absorbed by the Earth's surface, where it is transferred to the air and water through radiation, conduction, and convection. These processes create the complex patterns of wind, rainfall, and temperature that shape the Earth's weather and climate. Energy transfer is a constant and essential process in both the natural world and in human-made systems. Whether through conduction, convection, or radiation, energy moves between objects and systems, changing forms along the way and driving the physical processes that shape our universe. Understanding how energy transfers gives us insight into everything from the functioning of machines to the behavior of weather systems and ecosystems. It's a crucial part of the story of energy, helping us understand how the world works, both at the macro and micro levels. Energy is the driving force behind nearly everything we experience in our everyday lives. From the moment we wake up in the morning to the moment we go to sleep at night, energy is at work in countless ways, often without us even thinking about it. Whether it's the energy we use to power our homes, cook our meals, or move our bodies, energy is a constant presence shaping the world around us and making life as we know it possible. The energy we use daily comes in many forms, and it flows through every aspect of our daily routines. Understanding how energy is involved in these everyday activities helps us appreciate its role and the ways in which we can make better use of it. One of the most obvious ways we interact with energy is through electricity. Electricity powers the lights in our homes, runs our appliances, and enables our modern way of life. When we turn on a light switch, we're activating a flow of electrical energy through wires that ultimately powers the light bulb. Similarly, the energy required to run our televisions, refrigerators, computers, and air conditioners comes from the electricity that powers these devices. The electrical energy we use is typically generated at power plants through the conversion of other forms of energy. Whether that's burning fossil fuels, harnessing the power of wind or water, or using nuclear energy. Once generated, the electrical energy travels through transmission lines and is distributed to homes and businesses, where it is used to power countless devices that make modern life possible. The way we heat our homes is another common example of energy in action. Whether we use natural gas, electricity, oil, or even renewable energy sources like solar or geothermal, heating systems rely on the conversion of energy to warm our living spaces. In a typical gas furnace, natural gas is burned to release heat energy, which is then distributed throughout the home via an air or water. In electric heaters, electrical energy is converted into heat through a process called resistive heating, where an electric current passes through a resistor, causing it to heat up and radiate warmth. These heating systems rely on the principle that energy can change forms. Chemical energy in the case of natural gas, or electrical energy in the case of electric heaters, ultimately transforming into thermal energy to keep us warm. When we cook, we're also harnessing energy in various forms. The most common form of energy used in cooking is thermal energy, whether it comes from a gas stove, an electric stove, or even a microwave. In the case of a gas stove, natural gas is burned to produce heat, which then cooks the food. On an electric stove, electrical energy is used to heat a coil or a metal plate, which then transfers heat to the cooking pot or pan. In a microwave, electromagnetic energy in the form of microwaves is used to excite water molecules in the food, causing them to vibrate and generate heat. In all of these cases, the energy we put into cooking is ultimately converted into heat energy, which then cooks our food, making it safer and more palatable. Transportation is another area where energy plays a crucial role. Whether we're driving a car, riding a bus, or flying on an airplane, all of these forms of transportation rely on energy to move us from one place to another. Most cars today run on gasoline, a form of chemical energy that is converted into mechanical energy to power the engine and move the car. In electric vehicles, electrical energy stored in batteries is used to power an electric motor. Trains and buses typically run on diesel or electric energy, and airplanes rely on jet fuel to power their engines. In all cases, energy is being converted from one form to another. Chemical energy in fuel is converted into mechanical energy to move the vehicle. The energy required for transportation is substantial, which is why transportation is one of the largest consumers of energy worldwide. In our daily routines, we also use energy to charge our devices. Phones, laptops, tablets, and other electronic devices all require energy to function. When we plug our devices into a charger, electrical energy flows into the device and is converted into chemical energy in the battery. This chemical energy is stored and can be used later to power the device. Similarly, other gadgets and appliances such as electric toothbrushes, hairdryers, and vacuums rely on electrical energy to function. As we continue to rely on electronics in our daily lives, the energy used to power these devices becomes an increasingly important part of our overall energy consumption. Another aspect of daily life where energy is crucial is in the production and distribution of goods. Factories, mills, and plants rely on various forms of energy to manufacture products. Whether it's the electrical energy that powers machines, or the thermal energy used in processes like smelting or molding, energy is a vital component of the manufacturing process. In addition to production, energy is also essential for transporting goods from factories to stores and homes. Trucks, trains, and ships all require energy to move products across vast distances, ensuring that the goods we use in our daily lives are readily available. Even in activities that seem simple, like exercising or walking, energy is being used. Our bodies convert chemical energy stored in the food we eat into mechanical energy to move our muscles. When we eat, the food undergoes digestion, breaking it down into glucose and other nutrients that provide the fuel our muscles need. This chemical energy is then used by our bodies to power movements, from the smallest motion, like blinking an eye, to larger movements, like running or lifting weights. The energy we consume in the form of food is essential for everything our bodies do, from basic metabolic functions to intense physical activity. One of the most fascinating and increasingly important areas where energy is involved in daily life is renewable energy. As concerns about climate change and environmental degradation grow, the world is shifting toward more sustainable energy sources. Solar panels, wind turbines, and hydroelectric plants all harness natural, renewable sources of energy. Solar panels, for example, capture the energy from sunlight and convert it into electricity using photovoltaic cells. Wind turbines capture the kinetic energy of the wind and convert it into mechanical energy, which is then turned into electrical energy. Hydroelectric power plants use the energy of flowing water to turn turbines and generate electricity. These renewable sources of energy are becoming more integrated into everyday life as we look for ways to reduce our reliance on fossil fuels and decrease our carbon footprint. As we live our daily lives, it's clear that energy is at the heart of everything we do. From the electricity that powers our homes to the fuel that moves our cars, energy is involved in nearly every aspect of modern life. Works in these everyday processes, we can make better choices about how we consume energy, reduce waste, and work toward a more sustainable future. As technology continues to evolve, so too will the ways in which we use and harness energy in our daily lives, creating new opportunities for innovation and improvement. Energy is a powerful force, driving everything from the movement of atoms to the motion of galaxies. It fuels the processes that govern life, powers our technologies, and shapes the universe itself. But as much as energy is a central part of our understanding of the physical world, there are limits to how energy can be used, transferred, and transformed. These limits arise from the fundamental laws of physics, which place boundaries on what is possible within the realm of energy. Understanding these limits not only helps us grasp the true nature of energy, but also sheds light on the challenges we face in utilizing it efficiently and sustainably. One of the most important principles governing the limits of energy is the second law of thermodynamics, which states that in any energy transfer or transformation, some of the energy is lost as heat. This is a crucial aspect of energy that shapes the way energy behaves in real-world systems. The second law introduces the concept of entropy, a measure of disorder or randomness in a system. As energy is transferred or converted from one form to another, entropy tends to increase, meaning that energy becomes less useful for doing work. This is why no machine can be 100% efficient. Some of the energy is always lost as heat, dissipating into the surroundings in a form that cannot be harnessed for useful work. This inherent inefficiency is known as energy dissipation. In a car engine, for example, only a fraction of the chemical energy in the fuel is converted into mechanical energy to move the car. The rest is lost as heat, either through the exhaust or by warming the engine. In electrical systems, some energy is lost as heat due to resistance in wires and components. The same principle applies in nearly all energy systems, from industrial machinery to household appliances. While we can optimize systems to reduce energy loss, the second law of thermodynamics ensures that some amount of energy will always be wasted in every process. The limits of energy are not just about inefficiency, they also stem from the fundamental properties of matter and energy. The concept of energy conservation, as described by the first law of thermodynamics, tells us that energy cannot be created or destroyed, only transformed. While this law provides a powerful tool for understanding energy systems, it also places a limit on our ability to generate new sources of energy. We cannot simply create energy out of nothing. It must always come from somewhere. This is why, in order to power our world, we rely on a variety of sources such as fossil fuels, nuclear power, and renewable resources like wind and solar energy. Each of these sources involves the transformation of existing energy into a usable form, and the total amount of energy in the system is always conserved. The limits of energy are also apparent in the laws of motion and the behavior of particles at the smallest scales. In quantum mechanics, for example, the energy of a system is quantized, meaning it exists in discrete units, or quanta. This limits the ways in which energy can be distributed and transferred at the atomic and subatomic levels. The energy levels of electrons in an atom, for instance, are not continuous, but exist in specific quantized states. Electrons can only absorb or emit energy in fixed amounts, corresponding to the differences between these energy levels. This quantization of energy restricts the range of possible energy transitions within atoms and molecules, which in turn influences the way matter interacts with light and other forms of radiation. The uncertainty principle, a cornerstone of quantum mechanics, further emphasizes the limits of energy. This principle tells us that we cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely we measure one, the less precisely we can measure the other. This uncertainty has profound implications for our understanding of energy at the quantum level. It means that there are limits to how accurately we can predict and control the energy of a system, especially when dealing with small particles like electrons and photons. This inherent uncertainty places a fundamental limit on our ability to measure and manipulate energy with absolute precision. Another limit to the use of energy is the concept of energy degradation. As energy moves through systems and is transformed from one form to another, it tends to degrade in quality. High-quality energy, such as electricity, can be used to perform a wide variety of tasks, from lighting a room to powering a computer. However, once that energy has been transformed, say, into heat or work, it becomes less useful for performing additional tasks. The energy that is lost as heat, for example, can no longer be harnessed to do work. This degradation of energy is a natural consequence of the second law of thermodynamics, and it represents a fundamental limit on the efficiency of any system. The limits of energy are also evident in the realm of cosmology, where the concept of a heat death of the universe is often discussed. According to the second law of thermodynamics, over time, the universe will tend toward a state of maximum entropy, where all energy is evenly distributed and no more useful work can be done. In this state, all processes would cease, and the universe would reach a state of thermodynamic equilibrium. While this is a long-term theoretical concept, it highlights the ultimate limit of energy in the universe, the point at which all energy has become spread out and unusable. At a more practical level, the limits of energy are seen in the challenges we face in harnessing and using energy sustainably. Fossil fuels, such as coal, oil, and natural gas, have been the primary sources of energy for centuries, but they are finite resources. As these resources are depleted, we are left with the challenge of finding alternative sources of energy that can meet our growing demand. Renewable energy sources such as solar, wind, and geothermal energy are promising alternatives, but they also have their limitations. Solar energy, for example, is intermittent and depends on weather conditions, while wind energy requires suitable locations for wind turbines. Even though these renewable sources are more sustainable than fossil fuels, they are not without their own challenges in terms of efficiency, storage, and distribution. The transition to a sustainable energy future involves understanding these limits and working within them. We must find ways to maximize the efficiency of energy use, reduce waste, and develop technologies that can better capture and store energy. Energy conservation plays a critical role in this process, as reducing demand for energy is often as important as finding new sources of energy. In the end, while energy is a powerful force that drives our world, its limits are defined by the laws of physics, the availability of resources, and the efficiency with which we harness it. The limits of energy are not just theoretical, they shape every aspect of our world, from the smallest atomic interactions to the largest cosmic phenomena. Whether we are concerned with the efficiency of a machine, the sustainability of our energy sources, or the future of the universe itself, understanding the limits of energy is key to understanding the physical laws that govern the universe. As we continue to explore these boundaries, we will uncover new ways to use energy more effectively, but we will also have to confront the inherent limitations that come with this powerful force. As we look toward the future of energy, we are faced with a pivotal moment in human history. The energy challenges we face today are unlike any we've encountered before. Our growing population, technological advances, and increasing demand for energy have placed unprecedented pressure on the planet's resources. At the same time, the environmental impact of our current energy systems, especially those based on fossil fuels, has made it clear that we need to rethink how we produce, use, and manage energy. The future of energy, therefore, is not just about finding new sources of power. It's about creating a sustainable, equitable, and efficient energy system that can meet the needs of both current and future generations. The future of energy is inextricably linked to the rise of renewable energy sources. Solar, wind, geothermal, hydroelectric, and tidal energy all present exciting alternatives to traditional fossil fuels. These renewable sources have the potential to provide an almost limitless supply of energy without the harmful environmental effects of burning coal, oil, and natural gas. Solar power, for instance, harnesses the energy of the sun, which is abundant and available in nearly every corner of the planet. Wind power uses the kinetic energy of the wind to generate electricity, and both solar and wind power are becoming increasingly cost competitive with fossil fuels as technology improves and economies of scale come into play. As we continue to innovate and improve the efficiency of renewable energy systems, these sources are expected to play an even larger role in our energy future. For example, solar panels are becoming more efficient and cheaper to produce, allowing them to be deployed at a much larger scale. Wind turbines are also becoming more efficient, with larger turbines capable of generating more power. In the coming decades, renewable energy is expected to become the dominant source of power in many parts of the world, with solar and wind alone providing much of the electricity needed for homes, businesses, and industries. However, renewable energy sources come with their own set of challenges. Solar and wind power are intermittent, meaning that they don't produce energy all the time. The sun doesn't shine at night, and the wind doesn't always blow when we need it to. This variability requires us to find ways to store and manage energy effectively. One of the key innovations needed for the future of renewable energy is advanced energy storage technologies. Battery technology is rapidly improving, with companies and researchers developing more efficient, longer-lasting batteries that can store energy generated during the day for use at night or during periods of low wind. These advances in energy storage will be crucial for making renewable energy reliable and scalable on a global level. In addition to improving energy storage, the future of energy also depends on the development of smarter, more flexible energy grids. Traditional energy grids were designed to deliver electricity from large power plants to consumers. However, with the rise of decentralized renewable energy sources like rooftop solar panels and home wind turbines, the grid needs to become more flexible to accommodate these new forms of energy production. Smart grids, which use advanced digital technology to monitor and manage the flow of electricity, can better handle fluctuations in supply and demand, integrate renewable energy, and improve the efficiency of the entire system. This shift towards smarter energy grids will help ensure that energy is distributed more effectively, reducing waste and lowering costs. Another promising area for the future of energy is the development of nuclear fusion. Fusion, the process that powers the sun, involves fusing light atomic nuclei, such as hydrogen, together to form heavier nuclei, releasing an enormous amount of energy in the process. Unlike nuclear fission, which splits heavy atomic nuclei and produces dangerous radioactive waste, fusion has the potential to provide a nearly limitless supply of clean energy without the environmental hazards associated with traditional nuclear power. While nuclear fusion has long been considered a holy grail of energy production, recent breakthroughs in technology and research have brought us closer to making fusion a reality. If scientists can overcome the technical challenges of achieving controlled fusion, it could revolutionize the energy landscape, providing clean, abundant, and virtually limitless energy. While the focus of the energy future is often on new technologies, we must also consider the ways in which we can use energy more efficiently. Improving energy efficiency is one of the most effective ways to reduce energy consumption and lower environmental impact. Energy-efficient technologies, such as LED lighting, high-efficiency appliances, and electric vehicles, are already helping to reduce energy demand. In the future, energy efficiency will become even more important as we seek to decarbonize the economy and transition to renewable energy sources. By using energy more efficiently, we can reduce the overall amount of energy needed, making it easier to meet the demand with cleaner, renewable sources. In addition to technological advances, the future of energy also depends on changes in behaviour and policy. Governments, industries, and individuals all have a role to play in shaping the energy future. Policymakers must create incentives for the development and deployment of renewable energy technologies, promote energy efficiency, and invest in research and innovation. At the same time, individuals and businesses must adopt more sustainable energy practices, such as reducing energy consumption, investing in energy-efficient technologies, and supporting clean energy initiatives. The future of energy is a collective effort, requiring collaboration across all sectors of society. As we look to the future, it's clear that the world's energy systems are undergoing a profound transformation. The shift away from fossil fuels toward renewable energy, the development of advanced energy storage technologies, the rise of smart grids, and the potential of nuclear fusion all represent exciting possibilities for how we will meet the energy demands of tomorrow. But these advances will not come without challenges. The transition to a sustainable energy future will require substantial investment, innovation, and cooperation on a global scale. However, the benefits of a cleaner, more sustainable energy future are immeasurable, offering a world that is not only more energy efficient but also more resilient, equitable, and environmentally friendly. The future of energy is not just about new technologies or improved efficiency. It's about creating a world where energy is abundant, clean, and accessible to all, supporting a sustainable and prosperous future for generations to come. As we face the energy challenges of the future, we have the opportunity to reshape the way we think about energy, from a finite resource to a renewable, abundant force that can power the world without harming the planet. The choices we make today will determine the energy future of tomorrow, and it's up to all of us to take part in creating a better, more sustainable energy system for the future. The universe is an awe-inspiring place, full of mystery and wonder. While we've made great strides in understanding the fundamental forces and energies that govern the world around us, there remains a sense that energy is not just a scientific concept. It's something more, something that's deeply tied to the very fabric of the cosmos. From the dance of galaxies to the birth of stars, the universe seems to pulse with a kind of energy that is both tangible and elusive. Some even speak of the mystical energy of the universe, a force that transcends the laws of physics and connects all things in ways we don't yet fully understand. This sense of a deeper, more mysterious energy comes from the fact that, as much as we know, there are still phenomena that defy simple explanation. One of the most profound mysteries is dark energy, a force that, despite being responsible for the accelerated expansion of the universe, remains almost completely unknown. Dark energy makes up about 70% of the universe, yet it's invisible, intangible, and undetectable by conventional means. We know it exists only because of its effects on the expansion of space itself. As galaxies move further apart, dark energy seems to be pushing them away, acting like a kind of anti-gravitational force. But what exactly dark energy is, how it works, and where it came from, is one of the biggest unsolved mysteries in modern physics. Adding to the mystery is the concept of dark matter. While dark energy is responsible for the universe's expansion, dark matter appears to be the unseen mass that affects the motion of galaxies and other large-scale structures. Unlike regular matter, which interacts with light and can be seen through telescopes, dark matter doesn't emit, absorb, or reflect light. It's completely invisible to us. Yet we know it exists because we can observe its gravitational effects on visible matter. Together, dark energy and dark matter make up about 95% of the total mass and energy in the universe. Yet we know so little about them. They remain one of the most profound mysteries in all of science, an indication that there is much about the nature of energy and the cosmos that we have yet to uncover. On a more metaphysical level, The idea that the universe is filled with some kind of mystical energy is not new. Many ancient cultures and philosophical traditions have long believed in a life force or universal energy that connects all things. From the concept of qi in Chinese medicine to the prana of Indian philosophy, there has been a recognition for millennia that there is something more than just the physical world. In the modern world, this idea often finds its expression in the field of quantum mechanics, where the behavior of particles and energy is fundamentally interconnected. The mysterious nature of quantum phenomena, where particles can be in multiple places at once, where the very act of observation seems to influence the outcome, hints at a deeper, more mystical layer to reality. Even in the realm of physics, the search for a unified theory of everything, the elusive theory of everything, TOE, is driven by the idea that there is a single force that underlies all of the fundamental forces of nature. The TOE is the holy grail of modern physics, a single equation or theory that can explain everything from the smallest particles to the largest structures in the universe. Scientists have made tremendous progress toward this goal with the development of string theory and quantum field theory, which suggest that the forces of nature, gravity, electromagnetism, and the nuclear forces, may all be manifestations of a single underlying energy. If such a unified theory exists, it would revolutionize our understanding of the universe and energy itself, providing a framework for understanding how all of reality is interconnected. In the search for the deepest nature of energy, one of the most exciting ideas to emerge is that energy might not just be a product of physical interactions, but that it is woven into the very structure of space and time. According to theories in cosmology, the fabric of space-time itself can be thought of as a kind of energy field. This field can warp and stretch in response to the presence of mass and energy, shaping the way matter behaves. This is what we observe as gravity, the bending of space-time around massive objects like planets and stars. But what if space-time itself is alive, in a sense? A living energy field that not only responds to mass but also gives rise to the forces and particles that make up our universe? This idea is connected to the concept of quantum fluctuations. In empty space, where we think there is nothing, there is actually a seething, fluctuating energy that constantly produces and annihilates particles. These quantum fluctuations are part of the vacuum state of space, the nothingness from which particles arise. This suggests that even in the emptiness of space, there is a kind of energy at work. This vacuum energy is thought to contribute to the phenomenon of dark energy, which is driving the accelerated expansion of the universe. It's as if the universe itself is infused with a kind of latent cosmic energy that continues to expand and evolve, filling the universe with unseen forces that shape the course of cosmic events. Moreover, the very idea of consciousness and the role it plays in our understanding of the universe is linked to this sense of mystical energy. There is growing interest in the intersection between consciousness and quantum physics, particularly in theories that suggest consciousness might be an integral part of the fabric of reality. Some theories propose that consciousness itself could be a fundamental force or energy, influencing the way particles behave and even shaping the physical world. This idea, while speculative, raises fascinating questions about the relationship between mind and matter, and whether consciousness itself might be a manifestation of the same kind of energy that underlies the universe's physical processes. The mystical nature of energy also resonates with the idea of the interconnectedness of all things. Modern physics, especially quantum entanglement, reveals that particles can be instantaneously connected across vast distances as though they are linked, in a way that defies our classical understanding of space and time. This phenomenon, where the state of one particle is instantaneously related to the state of another, no matter how far apart they are, suggests that the universe may be much more interconnected than we can currently explain. It hints at a hidden energy that binds everything together, from the smallest particles to the largest cosmic structures. This interconnectedness is often viewed as one of the most mystical aspects of the universe, where everything is part of a greater whole, a cosmic web of energy that transcends space and time. As we continue to explore the universe and push the boundaries of our knowledge, the question of what energy truly is will continue to evolve, whether it's the mysterious dark energy that permeates the cosmos or the quantum fluctuations that give rise to particles. Energy is at the heart of the universe's most profound mysteries. It's clear that energy is not just a scientific concept, but also something deeply intertwined with the fabric of reality itself. It is a force that shapes the universe, connects all things, and continues to inspire wonder and discovery. As we delve deeper into the mysteries of energy, we may one day uncover truths that challenge our understanding of reality itself, truths that reveal the true, mystical nature of the energy that powers the cosmos. The relationship between energy and consciousness is one of the most profound and intriguing areas of exploration in both science and philosophy. While energy is traditionally understood as a physical quantity that drives the motion of matter, consciousness is often thought of as an intangible, subjective experience, something that arises from the complex interactions of the brain. But what if energy is not just something that powers physical systems, but also plays a role in the phenomena of consciousness itself? This question, though still speculative, has captured the imagination of researchers and thinkers alike, as it touches on the very nature of reality and the mind. To begin, it's important to understand that energy and consciousness, as traditionally understood, are distinct concepts. Energy is a measurable quantity in physics, associated with the ability to perform work, move matter, or create heat. It manifests in various forms: kinetic energy, thermal energy, electromagnetic energy, etc., and can be transferred, stored, or transformed. Consciousness, on the other hand, is a term that encompasses our awareness, thoughts, feelings, and perception of the world. It's a deeply subjective experience that has proven difficult to explain in terms of physical processes. Yet, there is a growing body of research that suggests energy may be more closely related to consciousness than we once thought. This idea is explored in various ways, including in the study of quantum mechanics, brain function, and even in the study of altered states of consciousness. One of the most fascinating areas of this exploration involves the idea of quantum consciousness. In quantum mechanics, particles like electrons and photons exhibit behaviors that defy classical physics, such as being in multiple places at once, superposition, or being instantaneously connected over vast distances, entanglement. Some theorists suggest that consciousness might arise from similar quantum phenomena in the brain. If the brain is operating in a quantum way, it may be that consciousness is, at least in part, a result of the interplay between energy and quantum processes. One theory that connects energy to consciousness in this way is the orchestrated objective reduction, or OR theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. According to this theory, consciousness arises from quantum processes that take place in the microtubules of neurons, the tiny structures within brain cells. These microtubules are thought to be capable of supporting quantum coherence, allowing quantum information to be processed in ways that classical brain activity cannot explain. In this model, consciousness is the result of energy dynamics at the quantum level, where the brain operates as a quantum computer, and the flow of energy through quantum states gives rise to our subjective experiences. This idea is still highly speculative, and there is no direct evidence that quantum processes in the brain are responsible for consciousness. However, it opens up intriguing possibilities for how energy might play a role in the emergence of consciousness. If quantum energy is indeed involved, it could suggest that consciousness is not just a byproduct of physical interactions, but is instead intricately tied to the fundamental properties of energy in the universe. This could mean that consciousness itself is a kind of energy, a form of energy that is not just tied to the physical body, but might be a fundamental aspect of reality itself. Another area where energy and consciousness intersect is in the study of brain function and neural activity. The brain is an incredibly energy-demanding organ, consuming a significant portion of the body's total energy. Neurons communicate with each other through electrical impulses, and the transmission of these electrical signals requires a constant supply of energy. The flow of energy in the form of electrical signals enables the brain to process information, form thoughts, and generate consciousness. This electrical activity is not only the result of chemical reactions, but also involves the movement of charged particles, creating electromagnetic fields. These electromagnetic fields are a form of energy, and their patterns may be related to the functioning of the brain at the most fundamental level. Some researchers believe that consciousness might be tied to the organization and coherence of these electromagnetic fields. It has been suggested that the brain's electromagnetic activity is not merely a byproduct of neural processing, but is an essential component of consciousness itself. According to this view, consciousness arises from the complex patterns of energy in the brain, with the electromagnetic fields generated by neural activity serving as the medium through which conscious experiences are organized and experienced. This idea proposes that consciousness is not just something that emerges from neural activity, but is in a sense a form of energy itself, arising from the intricate interactions of electrical and electromagnetic fields. Energy and consciousness are also connected in the context of altered states of consciousness. People experience altered states of consciousness in many different ways, such as through meditation, hypnosis, psychedelic substances, or sleep. These altered states often involve changes in the brain's electrical activity, and many researchers have observed changes in the patterns of energy within the brain during these states. For example, during deep meditation or certain psychedelic experiences, the brain can enter states of heightened coherence, where different regions of the brain synchronize their activity. These shifts in brain activity might reflect a shift in the way energy is organized and processed in the brain, leading to altered states of consciousness. The connection between energy and consciousness is also explored in spiritual and philosophical traditions. Many traditions, such as yoga, Buddhism, and Taoism, speak of a vital force or energy that animates the body and mind. In these systems, the energy is often referred to as qi or prana, and it is believed to flow through channels in the body, influencing mental and physical health. The idea is that consciousness is not just a product of the brain, but is a manifestation of a universal energy that pervades all of existence. This energy is often thought to connect all living things, and its flow is believed to be essential for maintaining health, well-being, and spiritual awakening. While these ideas are not typically part of mainstream scientific discourse, they resonate with the idea that energy and consciousness are deeply connected, and that consciousness may be a more fundamental force in the universe than we fully understand. In modern science, consciousness is often viewed through the lens of information processing and computation. The brain is seen as a complex information processing system, where neurons transmit signals that allow for the generation of thoughts, emotions, and perceptions. But even in this framework, energy plays a key role. The transmission of information in the brain requires the flow of energy in the form of electrical impulses, and the activity of these neurons is what gives rise to the experience of consciousness. In this sense, consciousness could be seen as an emergent property of the energy dynamics within the brain, a phenomenon that arises from the complex interactions of neural activity and energy. As our understanding of the brain and consciousness continues to evolve, it is likely that the connection between energy and consciousness will become clearer. While much remains to be understood about how consciousness arises and what role energy plays in its creation, the idea that consciousness is intricately linked to energy is an exciting area of exploration. It challenges the traditional view that consciousness is solely a product of neural activity, and suggests that consciousness might be a fundamental aspect of reality, linked to the energy that powers the universe itself. In the future, as our understanding of quantum mechanics, neuroscience, and consciousness deepens, we may uncover new ways to understand the connection between energy and consciousness. We may find that consciousness is not just a byproduct of the brain's electrical activity, but a more integral aspect of the universe, a form of energy that is woven into the very fabric of reality, whether through quantum processes, electromagnetic fields, or the flow of vital energy. The relationship between energy and consciousness is a mystery that lies at the very heart of science, philosophy, and the nature of existence itself. As we come to the end of our exploration of energy, it's clear that this concept is far more than just a fundamental force driving physical systems. From the smallest particles to the largest cosmic structures, energy is woven into the very fabric of the universe, governing the behavior of matter, shaping the processes of life, and providing the power that sustains everything we know. Our understanding of energy has evolved over centuries, from ancient ideas about the nature of motion and heat to the cutting-edge theories of quantum mechanics and cosmology. Throughout this journey, one thing has become abundantly clear. Energy is not just a resource or a tool, it is an essential part of the universe's structure and an integral force that connects all things. Energy exists in many forms, each with its own unique characteristics and behaviors. We've discussed kinetic energy, potential energy, thermal energy, and electromagnetic energy, among others. Each of these forms plays a vital role in the natural world, driving everything from the movement of planets to the chemical reactions that power life on Earth. But no matter the form, all energy is interconnected, constantly transforming from one type to another and always following the fundamental laws that govern its behavior. The law of conservation of energy, stating that energy cannot be created or destroyed, only transformed, remains one of the most important principles in science, reminding us that the total amount of energy in the universe remains constant, even as it flows and changes throughout time and space. The limits of energy are just as important as its vast potential. We've learned that the second law of thermodynamics places constraints on the efficiency of energy transfer, leading to the inevitable dissipation of some energy as heat. This inefficiency shapes everything from the operation of machines to the way the universe itself evolves. Yet despite these limits, the way energy flows and transforms continues to astound us. The energy we harness and use, whether in our homes, our transportation, or in advanced technologies like quantum computers, is only a small glimpse into the immense complexity of energy in the universe. As we've seen, energy is not only a physical concept but also a philosophical one. Whether in ancient spiritual traditions that speak of life force, or in modern theories of quantum mechanics and consciousness, energy is often understood as something more than just a tool for performing work. It connects all things, and in some interpretations it may even be the very essence of existence itself. From dark energy and dark matter to the potential links between quantum processes and consciousness, energy continues to elude our full understanding. The mystical nature of energy, the way it seems to underpin both the physical world and the most profound mysteries of existence, remains a fascinating area of inquiry. Looking to the future, energy will continue to be central to the challenges and opportunities that lie ahead. As we transition from fossil fuels to renewable energy sources, we're not just shifting the way we produce power, we're fundamentally changing our relationship with the environment and the planet itself. The development of more efficient energy storage systems, the growth of solar and wind power, and the potential of fusion energy all point toward a future where energy is both more sustainable and more abundant. But even as we innovate and progress, we will have to contend with the limits of energy, from the challenges of energy storage to the inefficiencies inherent in all energy transformations. Perhaps the most exciting aspect of our journey through energy is the realization that we have only scratched the surface of what there is to understand. The questions about dark energy, the quantum nature of consciousness, and the ultimate fate of the universe remain unanswered. As we continue to push the boundaries of science and technology, we will undoubtedly uncover new ways to harness and understand energy, leading to innovations and discoveries that we can scarcely imagine today. The future of energy is not just about finding new sources of power or improving efficiency. It's about rethinking our relationship with energy, exploring its deepest mysteries, and unlocking its potential in ways that will shape the course of human history. In the grand scheme of the universe, energy is not just a force or a concept, it's the foundation upon which everything rests. It is the key to understanding the past, present, and future of the cosmos. Whether it's the fusion at the heart of stars, the energy that powers the Earth's ecosystems, or the potential that lies within the atoms of matter, energy is what makes everything possible, and as we continue to explore its nature and its role in the universe, we will find that energy is not only the force that drives the universe, but also the key to unlocking its most profound mysteries.